So, some reminders of a few things here before we get started on the unit exam review. Okay, the unit exam is this Thursday. Okay, now that is also the day of one of the diploma exams. That means that learning support is unavailable. So if you normally have accommodations, okay, come and talk to me. I will do my best to provide them in the situation we're in. Okay, but you may not. You definitely won't be in learning support because they'll have the diploma exam writers in it, but I will try to arrange something else. Just come and talk to me today after class and we can set that up. Okay. Reminder also that this Friday is the last day to hand in any overdue assignments if you want them graded. Very shortly after 12:20 on Friday, I will post the Google form that allows you to register for the mock final. Okay. Remember that that is completely optional and you do not have to write it. Okay, it is, if you want, okay, you can do it. The Google form will ask you a few very simple questions. It'll ask you your name, okay? It'll ask you which unit exam, or actually which class you're in, okay? And which unit exam you would like me to replace with your mock final mark, should it be higher than that unit. It just saves me time, rather than having to look at all your unit exam marks, you're telling me which one to look at. Okay, and then it will ask you which writing time you would prefer. Okay, I need you to fill that out over the weekend. If any of those writing times become full, okay, priority will be given to those who register first. And I will talk to anyone who is kind of over the seating limit for this room at that particular day and time. I don't foresee that being a problem, but I have a contingency plan in place just in case. Okay, so you have to have it filled out over the weekend, okay, so that I can talk to anyone who I will have to reschedule on Monday. Okay. The plan for this week: we do Unit 4 exam review today. We do kinematics final exam review tomorrow. Dynamics unit exam review on Wednesday. You write your unit exam on Thursday. On Friday, we go over that unit exam. And then on Monday the 16th, we do the circular motion and gravitation unit exam review, or sorry, final exam review, and then we're done. Okay, that will be the end. Okay, questions on how things are going to go for the next week? For this unit, okay, the first thing we started with, obviously there's kind of two parts to this unit. There was the simple harmonic motion part, and then there was the wave part. Okay, so the first thing we went over was simple harmonic motion. Okay, that would be, okay, the things that might affect the period of a mass on a spring or the period of a pendulum. Okay, so that was those two formulas. We also talked about the nature of simple harmonic motion. Okay, in order for simple harmonic motion to occur, there must be what kind of force? Starts with R. A restoring force. That's what Hooke's law calculates. Okay? Hooke's law calculates the restoring force. Okay? The key thing, and this is something that could easily be tested in the multiple choice, is that for simple harmonic motion to occur, the restoring force must vary linearly, that's an R, linearly with displacement. That means the further from equilibrium the object moves, there will be linearly more restoring force. Okay, that has to be true for simple harmonic motion to occur. Okay. Oh, then there it was. I forgot I had that down below. Okay, restoring force must vary linearly with displacement. Okay, remember displacement in this unit is x, not d. Okay, then after that, we talked about Hooke's law. Okay, and as we said just a minute ago, Hooke's law calculates the restoring force. Okay? The force that is trying to pull the object back to equilibrium. Okay? And that is that the restoring force is negative k times x, specifically for a spring. Okay? Where k is the spring constant in newtons per meter, and x is the displacement in meters. One of the things we have to remember about Hooke's law and all simple harmonic motion is that x and F, so the restoring force and the displacement, will always be opposite in direction. That's why there's a negative in his formula. Okay? If I pull a spring to the right, the spring pulls to the left. Okay? That's the negative, that's the purpose of the negative. It will always make sure x and F are opposite in their vector. Okay? Hooke's experiment, okay, put the force in a spring equal to the weight that he had suspended from it. All right, so he hung all those springs from the ceiling, put weights on them, and measured how far they were displaced, knowing that the force of gravity was what was pulling against the spring. So the force in the spring was equal to the force of gravity. That, remember, is how scales work. Okay, whether they're a hanging scale or a bathroom scale that you step on, okay, all of them work the same way. You are compressing a spring, the spring is pushing against or pulling against the force of gravity. Okay, so in a case like that, where obviously it's gravity it's working against, you would set Hooke's law equal to the force of gravity. Okay? The other situation Hooke's law could be applied to would be to calculate the acceleration of the object, or if you were given the acceleration of an object while it was oscillating, okay, calculate its displacement, right? So in that situation, what we're saying is, in this case, the spring or the restoring force is the only force that is acting and is thus the net force. Okay? And then we could say that negative k times x equals m times a. Now, sometimes it's easy to get confused between a law of conservation of energy question, which we'll talk about next, and a Hooke's law question. They give you similar information. Okay? They'll give you spring constant. They'll give you displacement. Okay? How do you tell them apart? Will Hooke's law ever ask you about speed? Never. Speed is not on the board right now. Okay, speed is not part of Hooke's law. Acceleration can be, but speed will not be. Okay? Also, force is never part of conservation of energy. Okay? It's part of Hooke's law. Right? You have to kind of look for those kind of things. What does Hooke's law allow me to calculate? Forces, displacement, spring constants, accelerations. Yeah, I can calculate those things. I almost never calculate any of those things except displacement with a conservation of energy question. Okay? Another way to look at it, a Hooke's law question only ever asks you about one point in the oscillation. A conservation of energy question has to ask you to compare two. Right? Because the initial the energy at one point has to equal the energy at the other point. That's not true for Hooke's law. Okay? So that's how we can tell them apart. Okay? Everybody with me there? Okay. In simple harmonic motion, if we're talking about a pendulum, then the potential energy is gravitational. Okay? When we lift the pendulum away from equilibrium, we're giving it gravitational potential energy, and that's turning into kinetic as it swings through the arc. If we're talking about a mass on a spring, then we're talking about what kind of energy? What kind of energy does a spring or a bungee cord have? Elastic potential energy. Okay? Now, we talked about how we arrive or derive that formula. Okay? We know that work is a change in energy, and that work is force times distance. When we're talking about a spring, that force is the Hooke's law restoring force. Okay? So we know that we can calculate this force by going K times X. All right? Now, in its truest form, this is actually the average force. Okay? So not the maximum force and not the initial force, okay, but the average. Average is usually half of the maximum, so we would go 1/2 times kx to get the average. And we're multiplying that average force by displacement, which in this unit we use x for. So 1/2 k times x is 1/2 kx squared. Okay, that is average force times distance, or the work required to stretch or compress a spring, and thus the elastic potential energy that would be stored within it due to that work. Okay? So if we have a mass on a spring that is oscillating, that is the form of potential energy we use. If it's a pendulum, then we use gravitation. Okay? Which leads us to conservation of energy. Okay? Conservation of energy never changes. It is always the initial mechanical energy is equal to the final mechanical energy. Okay, which means our initial potential plus our initial kinetic equals our final potential. That's our final kinetic. Okay, which, as we said, for a pendulum would look just like a roller coaster question. M times G times H initial plus 1/2 MV initial squared equals MGH final plus 1/2 MV final squared. But if it's a mass on a spring, we substitute in the elastic potential or the gravitational potential. Okay, so remember, a conservation of energy question is going to ask for or give you speed. Okay, that is something Hooke's law questions will never ask for. Okay, and it is always going to give you 2 points of comparison. Now, at equilibrium, what kind of energy does the mass on a spring have? As it's oscillating and passes through equilibrium, it would only have what kind? Kinetic. Yeah, that's where it's going to be going the fastest, right? And at equilibrium, there's no force in the spring because X is 0 at equilibrium. So there can be no potential energy at equilibrium for either a pendulum or a mass on a spring. For a pendulum, the height would be 0 at equilibrium. At the maximum amplitude, it would only have potential, because at the maximum amplitude is where it stops and turns around and goes the other way. Okay, that's where X would be at its maximum, or it would be at its amplitude, A, okay, and it would only have potential energy. Things to remember, okay, for your unit exam. Because I might use terms like that instead of giving you X and giving you, okay, like V. I might just say at equilibrium or at its maximum amplitude. You need to know then what's going on at those points. All right, that was kind of it for the first half, okay, of the unit. Okay, so that's all there was. And you guys did well on the simple harmonic motion assignment. So, okay, go over that stuff, just refresh your memory. Okay, you guys know how to do that, okay, and you'll be fine for those kinds of questions on the test. Okay, I will ask you about period of a mass on the spring, period of a pendulum. Okay, I will ask you about Hooke's law, right? All of those kind of things. I will ask you a conservation of energy question. I guarantee all of those things are on there. Okay, in either the numerical or written response. Okay, multiple choice is going to ask you about the nature of simple harmonic motion, the nature of Hooke's law. Okay, but not calculations. Okay, then we moved into the wave portion of the units. Okay, remember that a wave is a traveling disturbance. A wave is energy, it is not matter. Okay, and a wave, as long as it's not light, requires what to travel? A medium. Okay, air, water, concrete, okay, wood, whatever, okay, a spring. It has to have something to displace, something to disturb, okay? Now, a wave carries energy from place to place. A wave can do work, okay? Remember the properties of waves. So that would be things like frequency, period, wavelength, amplitude, crest, trough, okay? I mean, on your quiz there, I made you identify the parts of a wave. Should you still know those terms for the unit exam? Absolutely. Will I give you a question like what was on the quiz? Probably not. But I'll expect you to know the terms, because I'll ask questions that say, you know, you got a crest here or you got a trough there. You need to know what that looks like. Okay. All right, so we got, okay, what would we call this distance from here to here? It is a crest. What's the distance called? The amplitude. It is the maximum distance from equilibrium. Okay, the same would be true down here. Okay, crest, trough, we're talking about the maximum amplitude. Okay, how many wavelengths from here to here? I will definitely ask this on Thursday. This is basically the definition of wavelength. Okay? One wavelength is the distance between any two successive points. Count them. How many wavelengths is that? 1.5. Right. This is one wavelength to here, and that's another half a wavelength. Okay? That is something you will have to be able to identify or draw. Okay, what kind of a wave is this? Because there were two kinds that we talked about. Two types were transverse and longitudinal. This is? Oh, it's a good thing you have a few more days before your test. This is a transverse wave. Okay, remember, in a transverse wave, the wave is going this way from left to right, but the medium is moving up and down, perpendicular or transverse or 90 degrees, okay, to each other. What kind of wave is this that has a compression, a rarefaction, a compression, and a rarefaction? John, what kind of wave is that?
Longitudinal.
Right, that's a longitudinal wave. Sound, remember, is a longitudinal wave. And in a longitudinal wave, the particles oscillate back and forth parallel to the direction the wave is traveling. Okay, that could definitely be a multiple choice question. Okay. So properties of waves, definitely got to know that. Okay. Then we talked about the universal wave equation. this is part of basically everything except the properties of waves in this unit. Being able to use V equals F times lambda or V equals lambda over T in a calculation, absolutely crucial. Okay? It's part of simple wave equation stuff, echoes, okay, you know, a tidal wave question, two boats in the ocean, okay? It's part of standing waves, it's part of air columns, okay? All of that stuff. So definitely be able to use that equation. Okay, so V equals F times lambda, or V equals lambda over T. Don't expect a 5-mark problem-solving question on the universal wave equation all by itself. What you should expect is a context-laden question involving the universal wave equation. Okay, one that you have to read carefully, okay, glean the important information from. Okay, the other part of universal wave equation has to do with that whole frequency never changes chestnut. Okay, that could definitely also be part of a context-laden question. Okay, that kind of question might seem like a lot of work, but in the end probably won't be. It's more about reading it and understanding what it's trying to get at. Okay, and then of course in an air column question, well, probably not a Doppler question, but okay, echoes, things like that. Okay, I would say universal wave equation in a context-laden question is probably more along the lines of a numerical response question. Okay, just because there's not a lot of work to do. Okay, if I tell you that there are 4 crests, how many wavelengths are there? I think you held up the right number of fingers. 3. Yes. Okay, there are 3 waves if I see 4 crests or 4 troughs. Okay, because that's 1 wavelength, that's 2 wavelengths, that's 3 wavelengths. Okay, the distance between any 2 successive equal points on a wave is 1 wavelength. There are only 3 cycles in 4 crests. Okay, is that the kind of thing I might put in a context-laden question? Like somebody's on a pier and they watch 5 crests go by, okay? And those 5 crests are X many meters apart, right? If you don't understand that 5 crests is 4 waves, are you going to get that question right? Okay. So definitely got to know that kind of stuff. Okay, interference. 2 kinds, constructive, destructive. Okay. Part of interference is the principle of linear superposition, which says when waves overlap, the amplitude of the medium will be the sum of the amplitudes of the individual waves. Okay? This was the question that went so sideways on the quiz the other day. Okay? Where I gave you a grid, right? And on that grid, I drew a wave like this, okay, and a wave like this. I think this was how it went. Okay, are those waves in phase? They are. When one is up, the other is up. Okay, I want to draw the resulting waveform. Is this constructive or destructive? Constructive. Okay, so if this is +1 and this is +3, where do I draw the resulting wave? +4. There would be my resulting waveform. Okay, I believe I told you after we did that question or went over that question that you would definitely see it again. You will definitely see it again. Okay, I promise you. It's not a threat, it's a promise. You will definitely see it again. Okay, be sure you know how to do a interference simple superposition question. All right. Also, oh, look at that. Same drawing. Okay. Also, 2-speaker question. Okay. Okay, I would expect to see one of those since you saw one on your quiz. Okay, there's not much to them, math-wise. Okay, maybe one of these calculations. Maybe. Okay, a Pythagorean theorem calculation for sure. Okay. A universal wave equation calculation for sure. And then deciding on whether or not the person hears a loud or quiet sound. Okay? In this situation here, 1.5 wavelengths from this speaker to the observer, 3.5 wavelengths from that speaker to the observer. Do they hear a loud or quiet sound? They hear a loud sound, because 3.5 minus 1.5 is 2. Okay, is that a whole number? Okay. Anytime that difference is a whole number, they are in phase. They are moving crest to crest, trough to trough. That person is hearing a loud sound. What if one side was 3.5 and the other side was 2? Then the difference is 1/2. That person hears nothing. Okay, quiet sound. All right, ringing a bell? Okay, definitely expect one of those as well. Okay, when a wave encounters a boundary, some of the wave will be, starts with T, means to go through into the next medium. Mark? Transmitted, yeah, transited, transmitted, yeah, close enough. Okay, it'll be transmitted, okay, and part of it will be reflected. Now, if it's going from a more dense, slow, to a less dense, fast, medium, the reflected wave will be upright. Okay, the transmitted wave will be longer or shorter? Remember, it was going from slow to fast, so it will be longer. Whatever speed does, wavelength does as well. The speed increases, wavelength increases, because frequency never changes. Remember that rule, okay? If you're ever in doubt, remember that rule and write it like this. F is V over lambda. If it can never change and V goes up, lambda has to go up as well. It's the only way F stays the same number. Okay? If frequency can never change, then the others have to change together in the same way. Right? How will that get tested? Pretty picture drawn by me. It's not going to be pretty because you know how well I draw. Okay, it'll be a diagram for sure. Okay, look at that diagram. Look at things like how far does the transmitted wave go compared to the reflected wave? Which way is the reflected wave? Is it inverted? Is it upright? All of those things can tell you whether one medium is more or less dense than another. Okay, so waves at a boundary, that's what we were just talking about. Also be able to identify all the behaviors of waves, okay? If a wave just, look, so if this is a barrier and a wave comes in, does this, and then goes off, okay, that would be what behavior? When something bounces off of something else? It reflects. Okay, don't forget about that law of reflection. The angle of incidence equals the angle of reflection. Okay, if I have a boundary like this and I have waves coming in, okay, that are very long, and then in the new medium, okay, they're very short, right? Has it gotten faster or slower? waves went from long to short. So they went from fast to slow. Okay, what is that called? It also starts with R. Refraction, right? That's why light bends when it goes into water. Okay, why diamonds are cut different than zircon, all that stuff we talked about that day. What would that be? Waves approach a narrow opening, and as they go through the narrow opening, they bend and become curved. It starts with D. That is diffraction. Okay? Diffraction. That's the thing that proved light was a wave and not a particle. Light can do that. Particles cannot. Okay? Now, something else we talked about when we talked about diffraction. Two things about a wave can affect how much it diffracts. Those two things are speed and wavelength. Okay? It was very hard to see light diffract. Does light go really, really fast? Does light also have a really, really, really short wavelength? Okay, those two things are why people thought light was a particle. The faster and shorter a wave is, the less it will diffract. Okay, anything that increases the amount of time the wave interacts with the opening will increase the amount of diffraction. So the longer and slower a wave is, the more it will diffract. Okay? That's why things cast a shadow. Light is fast and short. Okay? And so it does not diffract very much. All right, so make sure you know those wave behaviors and what waves do at a boundary. Standing waves. Okay, I made them on the slinky, right? Know the different names, like fundamental frequency, okay? Second harmonic, third harmonic, okay? Be able to identify how many wavelengths are in a picture of a standing wave. And obviously, universal wave equation plays a part in that. Okay. Okay, there's a standing wave. What frequency are we looking at? I'm not looking for a number. What's the name of this one? It is the first standing wave pattern you can get in any medium. Starts with F and it's not first. Fundamental. This is the fundamental frequency. Okay? It is the first harmonic. We never talk about that, but it is the fundamental frequency. Okay? Which one would that be? Okay, this is F1, this is the fundamental. What's that one? That's F3. Yeah, third harmonic frequency. Okay, if this is 100 hertz, what's the frequency that produces that pattern? 300 hertz. Okay, those are all things you should know. Okay, be able to determine. And obviously universal wave equation plays a part here as well. Okay, how many wavelengths are in the medium at the fundamental frequency? One half. Okay, there's half a wavelength there. How many at F3? Well, this is 1, that's a half. How many? 1.5. Got to be able to identify that, guys. I'm going to talk about those kind of things on the test. Okay, what's the name of these points? Antinode. What kind of interference is happening there? Constructive. Okay, so if I tell you a standing wave pattern is on a string and it has 5 antinodes, which frequency is it? F5. What are the areas of destructive interference called? Nodes. Yeah, okay, got to know those terms as well, guys. All right, so that's all standing wave stuff. Okay, so if I give you this, like this would be a perfect example of the kind of question I would give you. Okay, a string that is 6 meters long has the following standing wave pattern on it. What is the wavelength? Okay, so how many wavelengths here? 1.5. Okay, so that means 6 meters equals 1.5 wavelengths. Can we calculate the wavelength? Okay, it should be 4, right? Something like that. Yeah. Okay, that is certainly something I would ask. All right, then we looked at examples of standing waves, air columns. Okay? Inside our open and closed air columns, we would get standing longitudinal waves, okay, that result in resonance. All right, we saw what a standing transverse wave looks like when it resonates on the Tacoma-Narrows Bridge. Okay? You get a standing wave, you get large amplitudes, small amplitudes, antinodes and nodes. Okay? You get the same thing with a longitudinal wave, but you hear it instead of see it. Okay, so we have to remember that for a standing wave or an air column, okay, in a closed air column, our fundamental frequency has 1/4 of a wavelength in the tube, okay, which is why we use lambda equals 4L, okay, for a closed air column at its fundamental, and lambda equals 2L for a fundamental in an open air column. Okay, so here, this would make sound. That would be our F1. Lambda would equal 4 times the length of the tube. This would be F2. What do I hear at F2? Nothing. There's a node at the top. A node is an area of destructive interference, which is why closed air columns only resonate at odd numbered harmonic frequencies, F1, F3, F5, F7. Okay? It will not resonate at even ones because nodes will be at the top. Okay? You never get a node in an open air column. Okay? They resonate at all the frequencies. Okay? At the fundamental frequency, there's half a wavelength in the tube. At F2, a full wavelength. At F3, 1.5 wavelengths. At F4, 2 full wavelengths. Okay? And they will resonate at a wider range of frequencies. Okay, last thing we covered, Doppler effect. Okay, just know the formula. Okay, know what each part is. Okay, the formula is set up to solve for the Doppler frequency. Okay, F is the frequency you hear, you measure, you perceive. Okay, FO is the original frequency. Okay, the actual, the true frequency are some of the terms we use for that. V is the speed of the waves, in this case sound, and Vs is the speed of the source. When do you use plus? Object approaching or retreating? Retreating, yeah. I use minus when it's approaching. Okay, that's what's on there. All right, give you a few deets here about the test. Okay, there are 14 multiple choice questions, Mark. There are 5 numerical response questions. And there are 6 written. Okay, and in the written, those 6 questions amount to 28 marks. So that puts the whole test out of 47. Okay, any questions you guys have or anything you would like to go over in more detail? Okay. If not, here's my suggestion. You have the rest of class to prepare. I would look at the review package I posted on Friday, for starters. Okay, there's some fill in the blank there that can help you with a lot of the blanks you guys drew when I was asking you for terms today. Okay, so probably a good idea to look at those. Okay, fill in the blank questions. There's some problems as well. Okay, I don't know why this review package is like so much bigger than all the others. It just ended up that way. I don't know, I got on a roll. Yeah. Okay, so have a look over those. Okay, if questions come up or you want me to do a type of question on the board, I'm happy to do that. Okay, just ask and we'll go over whatever you guys ask for. Okay, let's make good use of our time.